They just need to give me change my permission. That's it.
Yes, ma'am. Now it's given.
Now it's there. Right. Yeah. Thank you. Okay. I hope my you're all able to see the screen.
Yes, ma'am.
Okay.
Yes,
Good.
yes,
Yes, ma'am.
Right.
yes,
So
ma'am. Yes, ma'am.
yeah, as I mentioned, the three key topics that we are going to look today is a review of what is a random variable, what we mean by a probability mass function, cumulative distribution function, notion of expectation and variance. Then we move on to some discrete distributions, and then we look at continuous distributions. So let's get started with the concept of a random variable. We have continuously seen when we reviewed probability concepts that the biggest building block of probability is what we call a random experiment. And the outcomes of this random experiment is what constitutes the sample space. Now, sometimes when we are performing a random experiment, we might not be interested in what are the outcomes of the experiment. For example, when I toss two coins, I know that it is going to be a head-head, head-tail. This is what I know is going to be my sample space. Head-head, head-tail, tail-head, and tail-tail. But sometimes I might not be interested in this. So let me share a whiteboard and okay, is my whiteboard visible? I'm writing something. Hello?
Yes,
Yes, ma'am. It is
Yeah.
visible.
Yes,
Okay.
ma'am.
So
Visible.
when
Yes,
I
ma'am.
have my sample space, it is head-head, head-tail, tail-head, and tail-tail. This is when I'm tossing the coin twice. I might not be interested in the outcomes of the experiment, but I might be interested about knowing what is the sort of number of heads that is coming up. For example, again, when I toss a roller die, I might not be interested in whether twice, I might not be just interested in knowing what is the outcome, but I might be interested in knowing what is the sum of outcomes. So what we are primarily trying to do or establish is, I want to associate with every outcome a real number. For example, if I'm counting the number of heads in this experiment, what is the number that I'm going to associate with this outcome? 2 heads. I would be associating 2 because I can count the number of heads. With this, I'll be associating the number 1. With this, I'll be associating the number 1. With this, I'll be associating the number 0. In other words, I am defining a random variable to be taking the value 0, 1, and 2. Similarly, when I actually have I'm tossing a coin twice, okay? In that case, what would happen is, let me share the entire screen so that I can move between this one. Is my PDF visible now? Are you all able to see the PDF?
Yes,
Yes,
ma'am.
ma'am.
Yeah. So you can see that when I roll a die twice, I have 36 possible outcomes. So instead of, I'm not interested in what is the particular outcome, but rather I might want to know what is the sum of the outcomes. So I might be interested in knowing how many outcomes result in the sum of outcomes is 7. Okay. Or the smaller of outcomes is 3. So what do we mean by this? So when I am trying to establish something of this kind, what we are trying to establish is the following. So you can see that when I have these, for example, when I have the this one and I'm looking at sum of outcomes, what is the sum of outcome 1, 1? I can map this outcome to what? What is the sum of this outcome?
2.
2.
2.
1, 2, it is 3.
3.
Similarly, 5, 6, this is 11.
11.
6, 6, it is 12.
12.
So you can see that I am mapping every outcome to a real number. Okay. And this is what we refer to as a random variable. A random variable is nothing but something that maps every outcome of your sample space to a real valued number. Is this clear, the first concept? So suppose I'm talking about sum of the numbers, then what are the possible value, and x is the sum of numbers. What are the possible values this x can take? With this, it is taking the value 2. With this, it is taking the value 3. Here, it is taking the value 4. Here, it is taking the value 5. And you can see that what is the value here? It takes value 11 and 12. So the possible values that x can take is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 up to 12. Is that clear? On the other hand, on the same sample space, if I define a random variable, say y, to be the lesser of the two values. So what is the value? And I say that if both the throws have the same value, it is going to be that value itself. So what is the value that is associated with 1 and 1? What is the value of 1 that is associated with 1? It would be 1 itself.
1.
What is the value that is associated with 1, 2 and 2, 1? Lesser of the values.
1.
1.
What is the value that is associated with 2, 2?
2.
2.
So if you look at this particular thing, now here you see what is happening is all these values, okay? In the earlier case, I had values that were being taken between 1 and 2. So for all these outcomes, what is going to be the value of y? For all these outcomes that I have marked,
1 to 6.
it is going to be 1. This is going to be 2. These outcomes, it's going to be 3. These outcomes, it's going to be 4. These outcomes, it's going to be 5. And this outcome, it is going to be 6. Is this clear? Yeah. So you can see that when I define x to be the sum of outcomes, okay, of the two rows, you can
Ma'am,
see
your
that
slides are not visible, ma'am.
slides are not visible. 1 second.
Whiteboard is visible, not PDF.
Okay, 1 second.
Yes, ma'am.
Now, is the slide visible?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes,
So now suppose I'm denoting x to be the sum of outcomes. You can see that x takes the values 2 to 12. Similarly, when I define it as the lesser of values, y takes the values 1, 2, 3, 4, 5, 6. Till here, is it clear?
Yes, ma'am.
Yeah.
Yes,
Okay.
Yes,
Now,
Yes,
if you look at, again, go back here, if I look at x, and which is the sum of values, so I know that the event or the outcome associated with x equal to 2 is 1, 1. Okay. X equal to 2 happens only with the outcome 1, 1. 3 happens with 1, 2 and 2, 1. 4 happens with 1, 3, 3, 1 and 2, 2. Okay. So I go back and I write with which value of x, what is the relevant event. I repeat, I write down with which value of x, what is the relevant event. Now, why are we doing this? Because I know what is the probability of an event. I have already defined what is the probability of an event. Okay, this I know from my probability classes. What is the probability of this event happening? That 1, 1 is happening. What is the probability of that
1
event?
by 36.
This
1
is
by
1 by
1 by 3.
36. Okay. So I am equating that the probability of this event happening is same as the probability of x taking the value 2. Similarly, what is the probability of x taking the value 3? It is the probability of this event happening. And what is the probability of this event happening?
1 by
36.
36.
It is 1 by 6, 36 plus 1 by 36, which is 2 by 36. Is that clear?
Yes, ma'am.
Yes.
Right? This is going to be 3 by 36. So if I write down the probability of all these events, that is equivalent to the probability of x taking that particular value 2 to 12. Till here, is it clear?
Excuse me, ma'am.
Pardon?
Yes, ma'am.
Excuse me, ma'am. I am having a doubt.
Okay.
How this value came of probability? 1 upon 36, 2 upon 36.
What is the probability of this 1, 1 happening? 1, 1 is that event happening, right? All the outcomes in the sample space are happening with equal probability. How many outcomes are there in this sample space? 36. So if you go back to and look at the probability tutorials, we have looked at the same example. In that, we have already looked at what is the probability of this event 1-1 happening. The probability of this event 1-1 happening is 1 by 36. The probability of this event 1-2 or 2-1 happening is 2 by 36. And that is equivalent to my probability x equal to 3 up to x is taking values 2, 3, 4, 5, 6 up to 12. So these are the probabilities with which x takes those particular values. Is this clear?
Yes, ma'am.
Okay. So now similarly, I can do the same thing for y. What are the values y is taking? Y is taking the value 1, 2, 3, 4, 5, and 6. So what is the event that is associated with y taking the value 1? You can see here I have already
1, 1,
listed
2.
this, right? All these outcomes are in that event, right? Now what is the probability of y equal to 1?
11 by
11 by
36.
36.
Equal to 1, 2, 3, 4,
11
5,
by
6, 7,
36.
8, 9,
1 by
10, 11.
36.
It's 11 by 36. Probability y equal to 2. 1, 2,
9 by
3, 4,
36.
5,
10
6.
by 36.
9 by 36.
36.
Probability y equal to 3.
And 7 by 36.
9 by 36.
7 by 36. And you can see that associated with on the same sample space, I have defined two random variables. One is the sum of outcomes and one is the lesser of the outcomes. And we have got what is called the probability mass function or distribution of this random variable. Is this clear? So
Yes,
here
ma'am.
what you
Yes,
see
ma'am.
on the
Yes, ma'am.
screen is the distribution of the random variable y. And what we had earlier is the distribution of the random variable x. Okay. But this is what now it is time for us to establish what is a continuous random variable and what is a discrete random variable. Now, a discrete random variable is a random variable that can take at most countable number of values. I'm not saying finite, I'm saying it's a countable number of values. For example, let's go back to the sample space for the experiment which we defined earlier. I am going to keep tossing a coin till I get a head. So what is the sample space for this experiment?
Infinity.
I am going to keep tossing a coin till I get a head. What would be the sample space?
Infinity.
It will be like
It can be
Number of-
H,
Going to be
it can
head.
be TH, it can be TTH, it can be
It is going to be
T 3 times and
TTH,
then
it is
H.
going to be TTTH, so forth, right?
Okay.
Agreed?
Yes,
Yeah.
ma'am.
Yes,
Yes,
ma'am.
sir.
Now
Yes,
I'm
ma'am.
telling the random variable is that toss when I'm getting the head for the first time. Okay. So what is the random variable associated with this outcome?
1.
One. This is
One,
going to
one,
be 2. This
two.
is going to be 3. This is going to be 4 and so forth. But I can count them. Is that clear?
Yes, ma'am.
Okay. So the discrete random variable is a random variable which can take at most a countable number of possible values. So always remember, if I am able to count, I have a discrete variable. On the other hand, if I have to measure, okay, a random variable which cannot be counted, but I have to measure, it would be a continuous random variable. So when I talk about a continuous random variable, it takes all possible values in an interval.
Excuse
A
me, ma'am.
continuous random variable typically involves measuring, whereas a discrete random variable typically involves counting. Now, when I, pardon? So at
Excuse
a
me,
cons,
ma'am.
yes?
I'm having a doubt. Can you explain again?
See, a discrete random variable is a random variable which can take values that can be counted. For example, if I'm talking about number of people in a household, do you count or do you measure?
Measure.
You count, you don't measure the number of people, right? But if I'm looking at temperature of a person, do I count the temperature or do I measure?
Measure.
Measure.
Weight of a person, do I count or do I measure?
Measure.
Measure.
speed of a vehicle, do I count the speed or do I measure the speed?
Measure.
You measure. Number
Height
of
of a person.
accidents in an intersection, do I count or do I
Count.
measure?
Count.
Number of spelling mistakes. So you can see whenever you are telling about number of something, you are counting it. That's why we are talking about countability. Is that clear?
Yes, ma'am.
Yes, ma'am.
On the other hand, when I talk about time, the total time you take, do you count the time? Total time. I'm assuming it's a continuous interval, right? I'm not telling in hours. If I'm asking you number of hours you have taken, I'm counting the number of hours. But if I'm asking what is the total time taken, are you counting or are you measuring?
Measuring, ma'am.
Measuring.
Small
Measuring.
doubt, ma'am.
Pardon?
Ma'am, I have a small doubt. Why time taken, time is directly also defined as a discrete value also, no, ma'am?
That's what I'm saying. If I am asking you number of hours taken or number of minutes taken and it's discrete, then it is okay. Otherwise, if it is, if I am allowing a continuous total time taken, it could be anything between 0 and 10 hours or 0 and 100 hours. Okay, it is continuous. I'm measuring the time. Is that clear?
Okay, ma'am. Clear.
Okay, ma'am.
How we are phrasing the question?
Yes, ma'am.
Yeah.
Ma'am, I have one small
It will be
doubt.
specifically
The age of a
given that
person.
the time is discrete.
Just a minute, please allow the person to complete who has asked before you. Yeah, please go ahead. One person who has
Yeah.
started the
Thank
doubt.
you,
Yeah.
ma'am.
Yeah.
Thank you, ma'am. I had a small doubt regarding the age. The age of a person is discrete, right? How is it
That's
continuous?
what I'm saying. See, if you are typically age of a person is calculated as number of years, right?
Yes,
Okay.
ma'am.
Yes,
But sometimes you can see that in many cases, in fact, they are saying that, okay, number of, typically that would be a discrete thing. When you're talking about age, it is, if you're computing it as number of years, it is fine. But sometimes you might find that people are saying number of age, months and days up to a particular day and everything. It depends on how you are measuring it. Are you measuring it right from the time you're born till now? Then afterwards, you do not know how you're representing that age, right? Is that clear? So it
Yes,
depends.
ma'am.
Typically, if it is number of years, it is discrete. So whatever that can be counted is as a discrete. That's what I'm trying to say. That's why you're defining it as a variable that can take countable number of possible values. Is it clear? Is
Yes,
the
ma'am.
definition clear?
Yes, ma'am.
Yeah.
Yes, ma'am.
So once I know
Are
what
we
is
going
the
to cover
discrete
important
and
questions
yeah.
on these topics? Are we going to
Pardon?
cover important questions on these topics?
I don't know how to answer this question. This is a review of the topics. Now, whether it is important or not important, you should decide. Okay, for me, any topic is important as a teacher.
I meant, are we going to cover important questions?
Pardon? I didn't get your question. I'm sorry.
Ma'am, I'm saying, are we going to cover important questions of these topics like week 9 to 12?
See, I am covering the concepts that has been taught. Okay, in week 9 to 12. Okay, and I believe every concept is important, so I'm just going to focus on all the concepts. Okay,
Ma'am.
Yeah.
Ma'am, if it's continuous, so it always comes under an interval.
Pardon?
If we take continuous random variable, will it always comes under an interval like a comma b?
Yes, a continuous random variable. That's what I said. A continual random variable cannot be counted, so it takes values along an interval that form an interval.
Okay.
So that's why you say that the probability of a random variable equal, a continuous random variable equal to any particular value is always assumed to be 0 because it belongs to a particular interval. You always say that x belongs to a particular interval and you look at the probability of x belonging to a particular interval. Is that clear? Whereas in a discrete, you're asking what is the probability x is equal to a particular value. That is the key difference. Is that clear?
Yes, ma'am.
So when I talk about a discrete random variable, the distribution of a discrete random variable is given by what is called a probability mass function. So X is a discrete random variable. X takes values x1, x2. Here I've written finite, but it could take any number of value. I can write it as takes values x1, x2, x3. So we have seen the value of tossing a coin till I get a head. It was taking value 1, 2, 3. It kept taking, but it is countable. Okay. The probability mass function lists in tabular form the value the X takes along with the probability it takes. Now, what are the properties of a probability mass function? When we look at the properties of a probability mass function, the first thing is, since it's a probability, it should be non-negative. The second thing is the summation of all the values of the probability should be equal to 1. These are the two key things. I repeat, the properties of a probability mass function is probability of xi is non-negative and probability of x equal to 0. For example, let's take x, which is taking the value -1, 0, 1. And probability of x is 1 by 3, 1 by 3, 1 by 3. Is it a probability mass function?
Yes.
Yes,
No,
ma'am.
no, 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 no.
Yes.
Why not?
Yes, ma'am. It is a
Because
probability.
because
It is a
because the
probability.
net probability sum is not equal to 1.
Well, it is 1 by 3, 1 by 3, 1 by 3. What is that? What is
No,
1
the
by 3 plus 1 by
probability
3 plus 1
is
by 3?
negative.
Oh, sorry,
Zero
I
point
missed
three,
that.
zero
I
point
missed
three,
that.
0.33.
It
It
is
is
taking
PMS.
value -1, 0, -1. But what is the probability mass function? It is. Now, suppose it was a 2 by 3 minus 1 by 3 and 1 by 3.
No.
No, ma'am.
No, ma'am, it is not.
Why not?
Because
Because
probability
it
can't
takes
be
negative
negative.
Sum
value.
2
is
by
not
3, 2
1.
by 3 and
Because
a
the
minus
total
1
sum
by
will
3.
be 2 by 3, no?
What about 2 by 3
Because
minus 1 by
probability
3
No,
and
cannot be
ma'am. It is
negative.
not.
Ma'am, it is
Probability
It
cannot be
cannot be
negative.
negative.
0.66,
even though it adds up to
0.66.
1, the probability cannot be negative.
Negative.
Is that clear?
Okay.
Okay, so some problems that you can get is to verify whether a particular function is a probability mass function or not. So at a conceptual level, you need to understand what are the properties of a probability mass function. Now, since I said that the probability mass function in a tabular form is x taking the value x1, x2, x3, so forth, with the probability p of x equal to x1, probability of x equal to x2. This resembles the frequency distribution. So I can graph this, right? The values of x on my x-axis. For example, here, what you see on the screen is the random variable x taking the value 1, 2, 3, 4. That is listed on the x-axis. The probability is on the y-axis, and the probability of x equal to xi is plotted as the bars. So this is what is called a probability mass function and the graph of the probability mass function. Now, what you notice here is the graph of the probability mass function gives us some indication of the distribution of this. For example, if you look at this, this is positively skewed. On the other hand, this is negatively skewed. Is that clear? And what about this? So suppose I had probability of x equal to x1, x2, x3, x4 with 0.25, 0.25, 0.25, and 0.25. What would be the shape of the distribution?
Symmetric.
It will be
It's
even.
going to be, everything is going to be the same, right?
Yeah, yeah.
Yes, ma'am.
It would be this way. Just cut off this. You can see that all of them, the heights of the bars are going to be the same.
Ma'am,
So
we
you
can
can
also
see,
call this left skew, right?
no, this is not skewed, right? It is symmetric. The
No,
earlier
no.
thing was
The earlier one.
this. Yeah. The earlier one, yeah. The right skewed and the left skewed. Okay. Right.
Okay.
Now, associated with the probability. So when we looked at it, we defined what was a random variable. We defined what was a probability mass function. You know, random variable is discrete. It is continuous. Associated with a discrete random variable, I have what is called a probability mass function, which is nothing but what is the probability with which x takes a particular value. Till here, is it clear to all?
Yes, ma'am.
Yes,
Now,
ma'am.
the next
Yes, ma'am.
important concept is that of a cumulative distribution function. As the name suggests, cumulative is nothing but I am accumulating. So I know what is a distribution function. The distribution function set probability x is equal to some value. So cumulative is what is the probability of x less than or equal to this value. That is why it is called cumulative. I am accumulating. So in general, this is a function which is mapping the entire real line because it's a probability to 0 and 1. Because probability will lie between 0 and 1. And this is defined for every value on the real line. So suppose I have a random variable which is taking discrete. I'd request everybody to please mute if you're not talking, please. Can you all please mute yourselves?
Online चल रहा है
I request everyone.
Rohit Kumar mute.
I think he's not aware that he's unmuted.
Prerna, can you please mute everyone so that they can unmute when they are asking a question?
Yeah, sure, ma'am.
Thank you. Okay. So if I have a random variable which is taking value x1 is less than x2 is less than x3. For example, if I have a random variable which is taking value 2, 3, and 4, and I know probability x equal to I, this is 1 by 2, this is 1 by 4, and this is, so I have 1 by 4. Is this a probability mass function? X takes the value 2, 3, 4 with these probabilities.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So what is f of 2? By definition, f of 2 is probability x is less than or equal to 2. Okay. So if I look at the entire real line, this is 0, this is -1, this is -2. I have a 1, I have a 2 here. Is that clear? I have a 3 here, I have a 4 here. The value of x, 2 is less than 3, is less than 4. What is the probability of x is equal to -2?
0.
0. X equal to -1?
0.
0.
X equal to 1?
0.
X equal to 2?
1 by 2.
So until probability x is equal to 2, this is going to take the value 0. Would you all agree? Till
Yes,
x is
ma'am.
equal to 2,
Yes,
I'm
ma'am.
just going to have the value
Yes, ma'am.
0. At x equal to 2, I have a jump of 1 by 2. Is it clear?
Yes,
Then
yes,
what
ma'am.
happens to it? This will remain at
Please
what is the
explain
probability?
again.
It will see what is the probability of x is less than or equal to minus. What is the probability x is equal to -2?
0.
-1, it's 0.
0.
It is taking the value 0 till this point 2, right? So what is the probability of x is less than or equal to 2? You add all the probabilities till x equal to 2. What do I get?
0
All
plus
of them
1.
is 0 only, right? At x equal to 2, what is the probability at x equal to 2? X is less than or equal to 2.
1 by 2.
It is going to be 1 by 2 because probability x equal to 2 is 1 by 2. Is that clear?
Yes, ma'am.
Yeah.
Yes, ma'am.
What is the probability x is less than or equal to 2.1?
1
by 2.
1 by 2.
It's again 1 by 2.
1 by 2.
2.2. It is again 1 by 2.
1 by
It will
2.
because it is less than, it is probability x is less than or equal to 2 plus probability, all of that, it is going to remain 1 by 2 till this point 3. Would you all agree?
Yes,
Yes,
ma'am.
ma'am.
Yes,
At
ma'am.
3,
Yes, ma'am.
what is the probability x is less than or equal to 3? That would include probability x is equal to 2
0.75.
plus this
0.75.
one. So it is going to
Yes,
be 3 by 4. So it again jumps. It will remain 3 by 4 till for some time, and x equal to 4, it is going to remain 1 throughout.
1.
This is the shape of a probability distribution function. Is this clear? So whatever you find here, these are the jumps. This is not a continuous distribution function, continuous graph. Okay, you find there are jumps. So this is what we refer to as a step function. Is this clear?
Yes, ma'am.
Yes,
Yeah. So a probability distribution.
Yes, ma'am.
For example, here, what is the probability till a is less than 1? It is 0, right? At 1, between 1 and 2, it takes the value 1 by 4. Agreed? X is
Yes,
less than
yes.
or equal to 2 is 1 by
Yes,
4 plus
ma'am.
1 by 2, which is 3 by 4.
Okay.
A is between 3 and 4 is 3 by 4 plus 1 by 8. That is 6 by 8 plus 1 by 8, which is 7 by 8.
7 by 8.
Yes,
So A is greater or equal to 4 is 7 by 8 plus 1 by 8. It is 1 and it will
1.
remain at 1. Since it's a
Okay.
probability, it is always bounded between 0 and 1. Is this clear?
Okay, clear,
Yes,
ma'am.
ma'am.
yes,
Yes,
ma'am.
ma'am.
Okay, this is the
Yes,
next important concept, and this is the graph of a discrete distribution. So the graph of a discrete distribution is a step function. Is that clear? And the size of the step, what is the size of the step? This was 1 by 4, this is 1 by 2, this is 1 by 8, this is 1 by 8. Is that clear? So you can see how this is 1 by 8. This is the size of this step. This is the size of this step. This is the size of this step. This is the size of, this is about 0.25. Okay. This is here. This is how we are getting it. Is that clear?
Yes, ma'am.
Yeah.
Yes,
Yes,
ma'am.
ma'am.
But is it always step function?
Yeah. For a discrete random variable, yes.
Ma'am, can you just explain the addition process of this one, ma'am, the cumulative distribution function of X?
You
How
need to
does
be
that-
louder, please.
Can you hear me now, ma'am?
Yeah.
Ma'am, can you just explain me how the addition of these values takes place in this f of a,
See,
ma'am?
let's look at this. I said when I write this for all other value, what is the probability x equal to 0 here? X is not taking the value 0. So what would be the probability x equal to 0?
0, ma'am.
0. X equal to 0.5. For any other value on the real line, what is the probability x equal to a? For any other a which is not equal to 1, 2, 3, 4.
0.
It's 0, right? Now I have a 1, I have a 2, I have a 3, I have a 4. All of them are on the real line. Is that clear?
Yes, ma'am.
So till this point, okay. So if I have till this point, okay, till this point, x equal to 1, what would be the value of all the points at this? This is going to be 0. So if I keep adding them, because cumulatively it is going to be add up all the probabilities till this point. So till this point, I'm going to get only 0. Because
Yes,
all the
ma'am.
probability of every value is 0, right? At x equal to 1, what is the probability of x equal to 1?
1 by
1 by
1 by
4.
4.
So
One.
this is the value, right? F
1 by
of
4.
1 is going to be 1 by 4. What will f of 1.1 be?
1 by 4.
That also 1 by
It's
4,
also
no?
1 by 4.
1 by 4.
So
1 by
for
4.
all the values between 1 and 2, it's going to remain at 1 by 4. What is
Yes,
probability
ma'am.
x is
ma'am.
less
Yes,
than or
ma'am.
Yes,
equal to
ma'am.
2?
1 by 2.
1
It
by
will be
4
1 by
less.
4 plus 1 by
1 by
2.
4.
1 by 4 plus
Accumulated. It's going to be 3 by 4, right?
Ah.
It will remain 3
Less
by
than or
4
equal.
between 2 and 3.
And if it's
At
like
3, I
x is
added. So
less
this will
than
be
2,
7 by 8. Then it will be 8 by 8. It will continue to be 1. Is that clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes,
Right.
ma'am.
So this is the shape of a step function. The important thing that we need to understand here is x1 is less than x2 is less than x3. If x is a discrete random variable with positive values with x1 less than x2 is less than x3, the distribution function is a step function. Okay.
Excuse me.
The next conceptual
Excuse me, ma'am.
understand. Yeah.
and if it's f p x less than 2,
Less than or equal to 2. Less than 2 would be same. So
same as
as
1,
long,
x is equal to 1.
yeah, it would be 1 by 4. If p of x is strictly less than 2, it would be between 1 and 2, right?
Okay.
It would be 1 by 4, that value.
Excuse me, ma'am.
Yeah.
Ma'am, if we write a probability of x less than or equal to 3, we will write a 1 by 4 plus 1 by 3 by 4. Otherwise,
No,
we
it
can.
won't be 1 by 4 plus 3 by 4. Less than or equal to 3 is 1 by 4 plus 1 by 2 plus 1 by 8,
1
which
by
is
8.
7 by 8.
No, I am saying that 1 by 4 plus 3 by 4 only we write. Yeah, we can
You
write
will not
only
write 1 by 4 by 3 by 4. See, what is it? What is the probability x is less than or equal to 3? You look at this table. What is it?
Okay.
It is 1 by 4 plus 1 by 2 plus 1 by 8, which is 7 by 8.
Okay, okay.
Is that clear?
Yes, ma'am.
Okay. Right. Yeah.
Ma'am, can there be a cumulative distribution function for continuous random variable?
Yes, but now we are discussing discrete. But I'll come to that when we are discussing continuous. Okay? Right.
Okay.
So the concept is, first we introduce what is a random variable. We are focusing now on discrete random variable. And then we introduce a concept of a probability mass function and then of a cumulative distribution function. The next important concept is that of an expectation of a random variable. Now what is, hello? Right. So suppose I am going to look at the way expectation is decided is, suppose X takes a value. Suppose I have a random variable. I'm tossing a coin once. I'm taking X. I have head and tail. I am associating value 1 with head and 0 with tail. So X takes the value 0, 1. What is the probability of X equal to 0? I'm assuming it's a fair coin. It is going to be 1 by 2. X equal to 1 is again going to be 1 by 2. So I can define expectation of X as this one suggests is the value I'm taking. So if I have X takes the value X1, X2, so forth, with probability X equal to Xi is probability X equal to X1, probability X equal to X2, and so forth. Expectation of X is the value multiplied by its probability. So what is expectation of X here? It is going to be 0 into 1 by 2 plus 1 into 1 by 2, which is a half. Is that clear?
Yes, ma'am.
Right? So suppose I'm having this one where I'm having HH, HT, TH, and TT. I already saw that X takes the value 0, 1, 2. What is the probability with which X takes the value 0? I'm counting the number of heads. What is the probability with which X takes the value 0?
1 by 2.
No. X takes the
1
value
by
0
4.
is equivalent to both tails.
1 by 4.
1 by 4.
1 by 4, ma'am.
X takes the value 1.
1 by 2.
2 by
This is
4.
2 by 4. And this is also 1 by 4. So what is the expectation of X in this case?
0.
It is going to 0 into 1 by 4 plus 1 into 2 by 4 plus 2
Plus
into
2 into 1
1
by
by 4.
1.
Right? What is it?
1.
It's equal to
1.
1. So what you notice here is, in this expectation of X is taking a value of X, whereas here expectation of X is not taking any value of X. So what is this X? So it is termed as a long run average. What do we mean by the long run average? If I say expect what is X in the first case, it is telling me whether it is 0 if I have a tail and 1 if it has a head. And I'm telling expectation of X is half. That doesn't mean that you're going to get an outcome which is half, because the outcomes can be only head or tail. But how do I interpret this half? The way I interpret this half is, if I keep tossing the coin for a long time, then on an average, 50% of the time I could expect a head and 50% of the time I could expect a tail. That's why I have an expectation of this X is referred to a long run average. If that random variable is repeatedly, I'm doing it in independent observation, the expectation of this X is what we term as a long run average. Is that clear?
Yes, ma'am.
The concept is expectation is a long run average. So it doesn't mean that expectation of X is half, or doesn't mean that half is going to be the outcome. That's not what it means. Is it clear? So let's apply the definition to something. Suppose I have X with probability 1. What is the expectation of X? X takes the value 0 with probability 1. What is the expectation of X? X takes the value 0. Probability of X takes the value 0 is 1. What is the expectation of X?
0 into 1.
0, ma'am.
It is 0. Okay.
Yeah.
Now Y takes the value -1 with probability half plus 1 with probability half. What is the expectation of Y?
Zero.
Zero.
And 0. Now Z takes the value minus 100 with probability half and 100 with probability half. What is the expectation of Z?
Zero.
Zero.
Okay, so now you find that expectation of X is equal to expectation of Y equal to expectation of Z, which is equal to 0. Right? But are they distributed the same?
No.
No, ma'am.
No.
No,
What is the difference? You see here X is taking only one value with absolute sure probability X equal to 0 is 1. Here you say it is taking the value between minus 1 and here it is taking the value between minus 100 and 100. So there is this concept of spread that is happening. There is no spread here. X is taking only one value here. So there is no spread. Here there is a spread which is having the highest spread. X, Y or Z?
Z, ma'am.
Z is having the highest spread. Y is having medium and X is having no spread. So just as we had variance as a measure of dispersion or a measure of spread in your descriptor, we need an equivalent measure here. And that is what we refer to as the variance of a random variable. Is that clear?
Yes, sir.
Okay.
Yes, ma'am.
Now, what is variance of a random variable? Suppose I denote the expectation of X by the Greek alphabet mu. The variance of the X is defined by X minus mu whole square. What is this X minus mu? X is the random variable. Mu is the mean or the expected value of the random variable. X minus mu is the distance between X and mu. This is the square distance. X minus mu whole square is in some sense the square distance, right? The expectation of X minus mu whole square is denoted as variance of X. Is this clear?
Yes, sir.
Yeah.
Yes,
Now, this variance of X, now you can also see that this X minus mu whole square, I can write it as X square plus mu square minus 2 times mu of X. Yeah, there is some question. Okay. So again, there are certain properties of expectation. What are the properties of expectation? Expectation of a constant times E of AX is A times expectation of X. Okay. Expectation of AX plus B is A. Expectation of X plus B. These are the properties. Is that clear?
Ma'am?
Right?
Yes, ma'am.
Yeah.
Yes.
Ma'am, can you give me an example for variance?
I've not finished telling it. I'll give you an example once I finish it. Okay? Is it clear? I'm not finished yet. So if I want to look at it, I have defined variance of X as expectation of X minus mu whole square. Till here, is it clear? Yeah?
Yes, ma'am.
Right?
Yes, ma'am.
So if when I have
Yes,
defined X minus mu whole square as expectation of X, I know this is going to be expectation of X square plus mu square minus 2 times this one. X minus mu whole square is this. Now I know that expectation of X plus Y is expectation of X plus expectation of Y. Similarly, expectation of X square plus Y square is going to be expectation of X square plus expectation of Y square. Expectation of X square plus A square is going to be where A is a constant, expectation of X square plus A square would be expectation of X square plus A square. Because expectation of a constant is itself. Is that clear?
Yes.
Yeah.
Right?
Yes.
Okay. Now mu is a constant because mu, I already know what is mu. So what is this? If I expand this, what is expectation of X square plus mu square? It will be expectation of X square plus mu square. Would you all agree? Because it's a constant.
Yes, sir.
Now,
Yes,
I also know
ma'am.
expectation of a constant times X is A times expectation of X. So this would be minus 2 mu times expectation of X. Till here, is that clear?
Yes, sir.
Yes,
But what
ma'am.
is expectation of X? I already know expectation of X is nothing but mu, right?
Yeah.
So I get here,
Yes,
this
ma'am.
is expectation of X square minus mu square. And that is an expectation. So the computational point of expect or the formula that is used to compute variance of x is expectation of x square, that is the expectation of the square of the random variable minus mu square. Is this clear? This is what we refer to as a computational formula for variance of a random variable. Any questions here? So now let's apply the concept. Let's look at some specific distributions. And for each of these distributions, we'll find out what is the probability mass function, what is the expectation of it. I again request people, please mute yourself immediately after you ask a question. Okay. Is that clear, please? Thank you. So for these specific distributions, we'll find out what is the probability mass function, what is the expectation, and what is the variance of the distribution. So let's start with a Bernoulli distribution. Okay. Now a Bernoulli distribution is a distribution or a random variable which takes the value 1 or 0. It takes only two values. It takes, what are the values it takes? It takes either 1 or 0. If the probability of x equal to 1 is p, what is the probability of x equal to 0?
1 minus 1.
1 minus p.
It is 1 minus p. So this is the probability mass function of a Bernoulli random variable. Now what is the expectation of this? It is going to be 1 into p plus 0 into 1 minus p. So what is the expectation of a Bernoulli random variable?
P.
It is p itself. So far so good? Okay. Now let's look at what is, if x takes the value 1 and 0, what are the values x square would take?
1 and 0.
That will also take 1 and 0. What is the probability with which x square takes this value? What is the probability with which x square takes the value 1?
Same
Again, that is
probability.
p.
P.
This is
Yes.
again 1 minus
minus
p.
P.
So what is expectation of x square?
P.
That's again p. Okay. Now I know what I know about variance of x is expectation of x square minus mu square, right? That is what I have here. What is mu? Mu is p, right? What is expectation of x square?
P.
P. So I'll get a p minus p square, which is same as p into 1 minus p. Okay. So the expected value of a Bernoulli random variable is p. And what is the variance of a Bernoulli random variable? It would be p into 1 minus p. Is that clear?
Yes, ma'am.
Okay. Now let's look at the next random variable, which is called a discrete uniform random variable. Now let me toss a roll a die. What are the values? I'm rolling a die once. What are the possible values I can have?
1 to 6.
1, 2, 3,
1, 2, 3, 4, 5, and 6. What is the probability with which it takes the value if it is a fair die?
1 by 6 for each.
1 by 6.
You can see that this is equal, right? So the value that the random variable takes, it is equally likely to take any one of the values 1 to 6. Is that clear?
Yes, ma'am.
Yes, ma'am.
So that's why this is called a discrete uniform random variable. It is taking discrete values and it is equally likely. So it is a uniform distribution. Now what is expectation of x here? It would be 1 into 1 by 6 plus 2 into 1 by 6 plus 6 into 1 by 6. I can remove 6 outside. What is 1 plus 2 plus 3 up to 6?
21 by 6, ma'am.
It is 6 into n into n. What is the sum of the first n?
N into n plus 1 by 2.
1 by 2.
N into n
Right?
plus 1 by 2.
Right. So what is the value of expectation of x?
21 by
N
6.
plus 1 by 2.
Which is 7 by 2.
7 by
which
2.
is 3.5. Is this
5.
clear?
Yes,
Again,
ma'am.
you can notice that
Yes,
this
ma'am.
expectation of x is 3.5, which is not a value that x is taking. That doesn't mean that when you roll a die, you're going to get 3.5 as the That is not what expectation of X means. It means that if you keep rolling a die sufficiently many of time, the expectation of that value is going to, that is in expectation, the mean of all these values would be 3.5, the long run expectation. Is that clear?
Yeah.
Yes.
Okay. So I
Yes,
can
ma'am.
extend this, I can generalize this to any value n. What I took as 6 values here, I can extend it and I can generalize it to any value. Is it clear?
Yes, ma'am.
Okay, right. The next thing I will talk about before I come to hypergeometric, I'll first introduce what is a binomial random variable, and then we'll come to hypergeometric. Now, suppose I already said what is a Bernoulli random variable. A Bernoulli random variable is typically anything that has two outcomes. So I'm talking about a head or tail, 1 minus p and p. Okay. Now, I'm tossing a coin twice. Okay. And what do I have? The first trial has again two outcomes, which could be head or tail. Second, again have head and tail. Suppose I'm tossing a coin thrice, it will again be head or tail. So what I am saying here is, these are, whether you're getting a head in the second outcome depends on whether you had a head in the first outcome or not. Suppose you're tossing a coin twice.
No,
Whether
ma'am.
you're
It is
getting a
independent.
head in the second outcome, does it depend on whether you had a head in the first outcome?
No, ma'am.
No, ma'am.
No, ma'am. It is
doesn't.
independent.
What is the chance that you'll get a head in the second outcome? Does that depend on whether you had a head in the first outcome?
No, ma'am.
No, ma'am.
Yes,
That's also independent, right? So this is what we call identical and independent trials.
Yes, ma'am.
Is it clear? D. Because the outcomes, okay, are identical and they are independent with the same probability of success or failure. Now, if I'm counting the total number of success in n such, again, identical and independently distributed, then x that counts the number of success in n trials is called a binomial random variable with parameters n and p. I repeat, x is in this case counting the number of successes in n. And what is most important here when I'm talking about a binomial, the identical and independent trial. Okay, we will talk about how this fails in another case very soon, but this is extremely important. Okay, now let's look at the following. Suppose I again have a sample space, HHH, HHT, HTH. I'm tossing a coin 3 times. What are the values I'm having? The outcome HHH. So let me write down all these outcomes. 1 second. Okay. Let me write down the outcome. I have HHH. I have HHT. I have HTH. I have THH. THH. Okay. Right. Then I have HTT. I have THT, I have TTH, and I have TTT. Is this right? These are the 8 possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8. Is this clear? Tossing a coin thrice.
Yes,
Okay.
Yes, ma'am.
Now in this, I'm counting the number of successes. In the first outcome, how many successes do I have?
3 successes.
3. In the second?
2.
Third?
2.
Fourth?
2.
2.
Fifth?
1.
1.
Sixth?
1.
1. 8?
0.
0.
Okay, so X is taking the value 0, 1, 2, 3. Now let's look at probability of this outcome happening. Okay, what is the probability with which I already know the probability of a head occurring is P and a tail occurring is 1 minus P. This is what I'm turning as 1 and 0. Is that clear?
Yes.
Probability of success is P. Probability of failure is 1 minus P. So what if, and they are independent of each other. The probability of success, each trial is independent and identical. So probability of this event or this outcome happening is probability of head happening in the first toss and the second and the third. What is the probability of head happening in the first toss? That is P. What is the probability of head happening in the second toss?
P.
P.
Third toss? P.
P.
So they are identical. If they are independent, what is the probability of head happening in the first, second, and third?
P cube.
Into
P
P
cube.
into P. Is this
P.
clear?
Yes, ma'am.
Yes, ma'am.
Now, what is the probability of this happening? First toss P, second toss P, third toss 1 minus P.
P into P into 1 minus
This would
P.
be P into 1 minus P into P. This is 1 minus P into P into P. This is P into 1 minus P into 1 minus P. This is 1 minus P, P, 1 minus P, 1 minus P, 1 minus P, P, 1 minus P, 1 minus P, 1 minus P. Is that right? So I have a P cube here.
Yes, ma'am.
I have a P square into 1 minus P square into 1 minus P square into 1 minus P into 1 minus P square, P into 1 minus P square, P into 1 minus P square, and 1 minus P whole cube. Is that right?
Yes.
Yes, ma'am.
So let's look at what are the values this X is taking? 0, 1,
0, 1, 2, and 3.
and 3. What is the probability with which X is taking the value 0?
1 by 8.
1 by 8.
1 minus P.
1 minus P cube.
1 minus P
Right.
cube.
What is the probability with which it's taking the value 1?
P into 1 minus
P
P.
into 1 minus
It
P
is
square.
P into 1 minus
into
P square.
1 minus
1
P.
minus P square into P, right? Taking the
ma'am.
value 2, it is P into 3 into 1 minus P into P square. This is P cube. Is that clear?
Yes, ma'am.
Yes, ma'am.
Right?
Yes, ma'am.
Okay. So now
Right.
so this is for X equal, so I have 3 tosses. Now if I have 4 tosses, okay, what are the values X would take? Again, how many
0 to
outcomes
4.
will I have? I'll have a HHHT.
0, 1, 2,
So you
3.
can see that what would happen, it is going to become P to the power of 4 and all of that, right? I could have all 4 heads. I could have 3 heads, 1 tail. I could have 2 heads, 2 tails. I could have 1 head, 3 tails. I could have all 4 tails. Is that right?
Yes, ma'am.
Yes, ma'am.
Yeah. So all 4 heads will happen with what probability? If P is the probability of success.
P
P
power
to the power
4.
of 4.
4.
This would be P to
Yes.
the power of 3 into 1 minus P, right? So
Yes.
you can see that if I have n trials, okay, the probability of all n successes is going to be P to the power of n. Would you all agree?
Yes, ma'am.
Yes, ma'am.
This is going to be
Yes,
P to
ma'am.
the power of n minus 1 into 1 minus P, right? And
Yes,
this is
ma'am.
going to be 1 minus P to the power of n. Is this clear?
Yes, ma'am.
Clear, ma'am. Clear.
Right? Okay.
ma'am.
So now if I want to know what is the probability of X equal to I, okay, for suppose what is the probability of, suppose I'm having 4, so I have X takes the value 0, 1, 2, 3, 4. I know that X takes the value 4 is all the heads. X takes the value 3. It could be head, head, head and a tail. It could be head, head, tail, head. So I need to choose where this tail will occur. Is that clear? And how many ways
Yes,
can I
ma'am.
do that?
4
How many
choose.
places? 4. And I can choose it. So the probability X equal to I, I can either choose the places head would occur or places where tail would occur. So that I can write as n choose I. Is that clear? Because I'm multiplying it with
Yes.
that. P to the I into 1 minus P to the n minus I taking value 0, 1, 2 up to n. This is what is referred to as the probability mass function of a binomial trial with n independent trials and P representing the probability of success. So far, so good. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Clear.
Okay. Now, if P is half, then you have a symmetric distribution. For example, here P is 0.3. You see it is not symmetric, n equal to 4 and p equal to 0.3. It is right skewed. If n equal to 0.5, is this symmetric? If p is 0.5, it is symmetric.
Yes, symmetric.
If p is 0.8, you see it is left skewed. Okay? Is that clear? Positively or negatively skewed depends on what is the value of your p. Now, as I keep increasing n, I took n equal to 4, I get this as the probability mass function. But if n equal to 40 and p equal to 3, you see where it is almost looking symmetric, but it is shifted towards the left. Can you see that? What is the mean? So now the next thing is, what is the mean of a binomial distribution? Okay. What is the mean or the expectation of a binomial distribution? The expectation of a binomial distribution is, I said that it is equal to the number of successes in n independent trial. Okay. I can represent this as x1 plus x2 plus xn, where xi is equal to 1 if trial I is a success and 0 if it is a failure. I repeat, each xi is a Bernoulli trial, where xi equal to 1 represents is with p and 0 with 1 minus p. Okay, so if I write it as x1 plus x2, if both the trials are success, what is the value x will take?
2p.
If 2, right? Would you agree? See, if x is x1 plus x2, what are the possible values of x1 and x2? It is 1 and 1, 1 and 0, 0 and 1, and 0 and 0. So if both are success, what is the value x would take?
2.
If one of them is a success, then what is the value to take?
1.
If both are failures, what is the value to take?
0.
0. Agreed? And this is precisely what I had as HH, HT, TH and TT, right?
Yes, ma'am.
Yes,
Both successes,
Yes,
both
ma'am.
failures, one of them is a success. If I toss 3 coins, it will be x1 plus x2 plus x3. All 3 of them are successes. What is the value x would take?
3.
3.
3.
One of them is a success. It could be either a 110 or a 101 or a 01 or a 011, right?
Yes, ma'am.
Agreed? And that value is 2. Is that clear?
Yes.
So the idea is I can express a binomial random variable as the sum of n independent Bernoulli random variables. Till here is it clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Now, if I have independent random variables, what is expectation of x plus y? I have already said this. What is an expectation of x plus y?
Expectation of x plus
Expectation of x plus expectation of y.
Expectation of y. So what would expectation of x be in this case, where x is x1 plus x2 plus xn?
nx.
N times
It is expectation of x1
x1
plus expectation of x2
expectation
plus
of
expectation of xn. Each xi is a Bernoulli random variable with parameter p. What was the expectation of each xi? If each xi is a Bernoulli with parameter p, what is expectation of a Bernoulli random variable?
N times
P.
It is p, right? Okay.
Yes.
So what would I get here? What is expectation of x1? It will be p plus p plus p. How many times am I adding it?
np.
So I get expectation of a binomial random variable is n into p. Is that clear?
Okay, ma'am.
Yes, ma'am.
Yes, ma'am.
So, ma'am,
Right?
it basically follows IID, right?
Yeah, a binomial distribution meets the IID condition.
Okay.
Okay, if that IID is not there, that's why when we go to hypergeometric, you'll see why it fails. Okay.
Yes, ma'am.
Similarly, if I have independent random variables, variance of x plus y is variance of x plus variance of y. Independent. Okay. What is the variance of each xi? We just saw that. If xi is a Bernoulli, what is the variance of a Bernoulli random variable with parameter p?
P into 1 minus.
P into 1 minus
1 minus P.
So what would variance of x be here? It would be variance of x1 plus variance of x2 plus variance of xn. Agreed? So
Yes,
what
ma'am.
would
Yes, ma'am.
and what is the variance of each xi?
P into 1 minus
P into 1 minus
P into 1
So
minus
what
P.
would variance of x be?
n times p into 1 minus p.
n times p into 1 minus p. Is this clear?
Yes, ma'am.
Yes,
So
ma'am.
you can see that when I'm talking about a binomial random variable, the expectation of a binomial random variable is n into p, and the variance of a binomial random variable is n into p into 1 minus p. When I talk about a binomial, I need independent and identically distributed Bernoulli trials, where a Bernoulli trial has only two outcomes, which I'm terming as success or failure. Success happening with P. What is failure happening with 1 minus P?
1 minus p.
Is this clear?
Yes, ma'am.
Yeah.
Yes, ma'am.
So the limitation
Yes, ma'am.
is this independent and identically distributed. For example, now let's look at this example on the screen. Okay. I am actually looking at, suppose I have a box with 4 white balls and 3 blue balls. Okay. Let me describe this experiment now. Carefully listen to it. I am picking up one ball, noting the color and returning that ball to the same box. Okay. I am picking up another ball and noting the color. I'm doing 2 times the experiment, 2 trials of
Yes,
the same
ma'am.
experiment. I am
Yes,
picking up the ball, noting the color, keeping the ball inside the box. I'm doing the second trial, again picking up a ball, noting the color and keeping it again. Are my trials independent of
Yes.
each other?
Yes, ma'am.
Is
Yes, ma'am.
is the
Yes.
probability or chance of picking a white ball identical in every trial?
Yes.
Yes, ma'am.
No. Yes,
So I
ma'am.
have an identical and independent experiment in that case.
Yes, ma'am.
Yeah.
Now I'm changing the experiment.
Yes, ma'am.
I am picking up a ball, the first trial. If I find a black ball, I am not replacing that ball. So what would happen to this box? If I have a black ball,
Number will reduce.
Number of
I
black
have
balls
4
will
white and
reduce.
2
Black
black,
will reduce.
right? If it is a white ball, it will become 3 white and 3 black.
Yes, ma'am.
Yes, ma'am.
Yeah. What was the
Yes,
chance
ma'am.
of me getting a black ball in this first trial?
3 by 7.
3 by 7.
What is the chance of me getting a black ball in the second trial?
2 by 6.
2 by 6.
So what is the chance of me getting a white ball in the first trial?
4 by
4 by 7.
What is the chance of getting a white ball in the second trial?
3 by
3 by
6.
6.
You can see that the chance of getting a black ball in the second trial depends on whether you had a black ball in the first trial or not, because this is 3 by 6 and this is 2 by 6. Similarly, this is 4 by 6 and this is 3 by 6.
Yes, ma'am. It
Yes,
depends.
So
ma'am.
here you have a case of not independent and not identically distributed. Is it clear?
Yes,
Yes.
ma'am.
Yes, ma'am.
Yes, ma'am.
So you first one, when I replaced it, I had a case of identical and independent. Now because whether it's a black ball or not depends on whether it was a black or a white ball in the first trial. Would you all agree?
Yes,
Yes,
ma'am.
ma'am.
Yes,
Yes, ma'am.
Okay. So in this case, I have trials that are not independent, and the probability of getting a black ball is not the same for all trials. So I cannot apply the binomial distribution here. Is this clear?
Yes,
Yes, ma'am.
ma'am.
Okay. So now let's introduce what is called the hypergeometric distribution. In the hypergeometric distribution, okay, I need the random variable. Again, I have a fixed number of trials, just as I had in the binomial distribution. But what is happening here? The probability of success is not the same from trial to trial. In my binomial, it was same.
Yes, ma'am.
Is that clear?
Yes, ma'am.
Now again, I am defining the number of successes out of the number of items chosen. So I will demonstrate it using this graph. So suppose I have n items totally. total number of balls are n. Okay, of which I have m which are blue and n minus m which are white. So in the earlier case, my total number of balls were 7. I had 3, that is m equal to 3, and I had 4 white balls. Is that clear?
Yes, ma'am.
Yes,
Okay. Suppose I am choosing 3 balls out of the 7 balls. Okay. I'm choosing 3 balls out of the 7 balls. Now, what are the colors that these 3 balls can take? What are the possible things for the 3 balls?
Yeah, 3 white, 2 black,
Can all
2
of them
white.
be black?
Yes, ma'am.
Yes.
Yes, ma'am.
Can 2 be black and 1 be white?
Yes, ma'am.
Yes, ma'am.
2 be white and 1 be black?
Yes, ma'am.
Yes.
Right?
Right combination.
1, all 3 white?
Yes, ma'am.
Yes, ma'am.
What you can see is the similar of all 3 heads, 2 heads and 1 tail, 2 tails and 1 head, and 3 tails. It's similar to this, but what is the difference between these two? Here I had IID, here it is not IID because I am doing it with, when I'm doing it without replacement.
Replacement.
Is the idea clear?
Yes, ma'am.
Yes, ma'am.
Okay. So now I want to know what is the probability of x equal to x, where I am looking at the number of black balls chosen. Again, what are the values this x can take? It can take the value 0, 1, 2, and 3.
3.
Okay. But what would be the probability? How many ways can I pick up 3 balls from 7 balls?
7 C3.
7 choose 3.
That would be my denominator. Agreed?
Yes, ma'am.
Okay, right. Out of these 3 balls, okay, I want x balls to be, so I want from here, I have this n choose n, right? Out of this, how many of them would be black balls? What is the chance that I'll have from 2 of them are black balls?
3
And one of them
3
is a
choose
white
2.
ball. I'll
3
have
choose 2.
3 choose
4
2
C1.
into 4
4
choose
choose
1.
1.
Is that right? And that is this
Yes,
m
ma'am.
choose x and n minus m choose n minus x. Is that clear now?
Yes, ma'am.
How the hypergeometric distribution has been got?
Ma'am,
Yes, ma'am.
Yeah.
small
Yeah.
n represent.
Hmm?
What is small n?
Small?
N.
It can, small n is the number of balls I'm choosing. From the 7, I'm choosing 3 balls.
So it is given or
Yeah, I'm choosing. So for example, if I tell that I'm randomly selecting small n items without replacement from a set of capital N items, right?
So
Okay.
capital N is the population and small n is the sample from which it is taken.
I'm just, don't get confused with population or sample. I have suppose 10 here and I'm choosing 5. Okay, and out of this 10, I have 6 and 4. Okay, what are the possible values that we can take now? Now tell me what are the possible values. I'm choosing 5 balls from 10 balls. What are the possible values B can take? X is the number of black balls in this 5. What are the possible values B can take?
0 to x.
0 to
What does x
0
equal
to
to
n.
0 mean?
X equal
No
to 0
black
means
balls.
there's no black balls.
No black balls.
So what should all of them be?
White.
All of them should be white.
But how many white balls do I have?
5.
We have only 4 white balls.
It's not
You get the point?
possible. It's not
Yes,
possible.
minimum 1.
yes,
Yes.
ma'am.
Okay.
It should be
So
from 1
then
to 5.
X would start
It
with
is
1,
1 to
right?
5.
1 to 5. Yes,
X2,
ma'am.
1, 2, 3, 4, 5. Is that clear? How to, here it's general. If again, if it X can take the value 0, this would be the thing. Otherwise, you should work out with X equal to 1, 2, 3, 4, 5. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yeah. Saikat, what is your doubt?
Ma'am, in the lectures we have taught that x should be greater than equal to m plus n minus capital N.
Yes.
What does
But
that mean? I didn't understand.
that's why I gave this example now, right? Suppose I am having 10 balls and I have m equal to 6 and n minus m equal to 4. Okay, this formula, what we have as x equal to 0, 1 to n, would work only when can x take the value 0 when I'm choosing 5 balls here. Can x take the value 0 now?
No.
No.
Right, that's why I had that formula. Is that clear?
Okay.
Yes.
Clear.
Yeah, that's why. Yes, Abhimanyu. Abhimanyu? Okay, is that clear? So that's why I
Yes,
had
ma'am.
the condition to make, because if I'm giving a general formula, that condition would work only under that case, right? See, now x does not take the value 0. Whereas here I specified x takes the value 0, 1 to n. And the reason I specified this is when I talk about a binomial distribution, I have x taking value 0, 1 to n. But then I have identical and independent distribution. Here I do not have, I lose that. It is without replacement. Is that clear?
Yes, ma'am.
Clear.
Yes, ma'am.
Yes, ma'am.
Okay. But let's look at the distribution. Okay. So now you can see that here, what is the value of x? So you can see that here again I have 2 x equal to 1. Again, these two BW and WB x equal to 1. Both W x equal to 0, and you can see x again takes the value 0, 1, 2. Okay. And this is the example I have here, where n equal to 7, n equal to 2, and m equal to 3. You can see the value of I equal to 0, 1, 2 with this probability. Okay. Now, if you look at the expectation of a hypergeometry, without going into the details, because we don't have the time for the details now, the expectation of x is n into m by n. The variance of x is n into m by n. I'm just going to break this into this thing to just give you one particular thing. I'm going to write this as n into m by n. Here I'm going to write it as n into m by n. This one I'm going to write it as n into 1 minus n by n. Okay, this term I can write it in this way. Would you all agree?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Right? I can do this, right? I'm writing n minus m by n. So I get that. No, sorry, this would be 1 second. 1 second. I'm going to write this as n into m by n. Okay. This I'm going to write as n into m by n. I'm going to take n outside. Okay. If I take n outside, I'm going to get 1 minus m by.
Ma'am will not take n outside, right? It will be 1
I'll
minus m
write
by
it
n.
as 1 minus n by n. I'm going to, the n will not be there. Okay. And this again, I'm going to take 1 n. N cancels out. I can do this.
Yes, ma'am.
Yes,
Is
ma'am.
that right?
Yes.
Do you all
Yes, ma'am.
agree?
Yes, ma'am. Yes, ma'am.
Now, if n is very, very small as compared to capital N, so what would happen? What do you think is going to happen? Suppose this, if I'm writing this m by n, and n is very, very small as compared to n,
Then 1
with
only.
this capital
It
N,
becomes
these
0.
two in some sense it is going to become 1. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
In that case, you can see that this is n into m by n. This is n into m by n into 1 minus n by n. Do you see a recognition to np into 1 minus p?
Yes, ma'am.
Yes, ma'am.
This
Yes,
is the
ma'am.
expectation and variance of
Yes,
a
ma'am.
binomial random variable. Agreed?
Yes,
So
ma'am.
if you
Agree.
go back
Yes,
and
ma'am.
see, this is the graph of a
Excuse me, ma'am.
hypergeometric distribution. Now let me compare this with binomial. For n equal to 5, the blue one is binomial, the red one is hypergeometric. You just look at n by n because I want you to look at n by n because n by n is what I have here. Is that right? If n by n is very, very small, 1%, you see this is what is happening. You see this is how so you can see that the hypergeometric and the binomial are almost same if this n by n is very, very small. That's what I want you to see. Is that clear? You can see that the distributions are almost
Yes.
the same.
Yes,
Is it
ma'am.
clear?
Yes, ma'am. Yes, ma'am.
Okay, that's what's happening. But the minute it becomes 10%, you see there's slightly difference. When it is 5%, 50%, you see the hypergeometric is very different from the binomial. Is it clear?
Yes,
Clear,
As
ma'am.
long as this
Yes,
n by
ma'am.
n was very small, they were almost the same. Is it clear?
Yes,
You
ma'am.
can still
Yes.
answer corrections. Yeah. And another thing which you notice here is as this n increases, the shape of both the distribution is more symmetric and bell-shaped. You notice that? Okay, these are some observations that you have here. When you do your stat 2, this would actually lead to what is called the sampling distribution and the central limit theorem. But at this point of time, you can just see and look at what is happening to the shapes. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. The last discrete distribution that we are going to discuss is what is called the Poisson distribution. Again, remember when I talked about a discrete random variable, I said you're counting the number of something happening. Binomial, it was number of successes in n trials. Even hypergeometric was the number of successes in n trials, but there you are not having sampling without replacement and with replacement. In Poisson distribution, you are counting the number again, but here you are counting the number occurring either in a fixed interval of time or space. I repeat, you are counting the number of events that are occurring either in a fixed interval of time. For example, if you are counting the number of vehicles that are passing through a traffic intersection between 9 a.m. and 12 a.m. There's a fixed interval of time.
Yes,
Yeah,
ma'am.
9.
Yes,
Yes, ma'am.
And what are you counting? You're counting the number of
number of
vehicles passing.
Vehicles.
Okay, number of deaths happening in a particular interval. Number of spelling mistakes in a particular book. Okay, that is an interval of space. Is that clear? So the number
Yes, ma'am.
of times this happens in a fixed interval of time or space is what we refer to as a Poisson random variable. It is also a discrete random variable. Okay. Now this we say that X follows a Poisson distribution with parameter lambda, where this lambda is basically, it is telling us where the events are happening with a known average rate lambda. Is this again clear?
Yes, ma'am.
Yeah.
Now, for example, if I am talking, now let me give you two examples. I am looking at a store. Okay, I am telling you people buy with probability 0.25. I want to know out of 10 people, okay, if 100 people visit a store, I want to know what is the chance that 10 people actually buy. People buy with probability 0.25. Okay. Listen to the problem. I'm saying there is a large store. The probability of a person making a purchase is 0.25. On a particular day, 100 people enter the store. What is the chance with which 10 people have actually made the purchase? What is the distribution that you would use?
Awesome.
Poisson distribution.
Poisson? Why will it be Poisson? What is the question I'm asking?
Because it is in a fixed interval of time.
But what is, so if I'm telling you that out of, okay, let me ask you the first question. I have 10 people visiting a store. Each person is making a purchase or with independently of each other, and the probability that a person makes a purchase is 0.25. Okay. What is the chance that three people make the purchase? It is binomial because I have, I recognize it as a binomial for this one, and it is a binomial with parameter n equal to t, p equal to 0.25, and I'm asking what is probability x equal to 3. Is it clear?
Yes, ma'am.
Clear.
On the other hand, if I say that the probability of people making a purchase or the event, purchase is the event is happening at a rate, say lambda equal to 2 or something, 2 per hour people purchase, what is the chance that exactly 3 people make a purchase? Then that would be a Poisson distribution. Is that clear?
Yes.
Clear.
Okay.
Yes,
So
ma'am.
that is where, for example, when I'm having number of vehicles or number of typos, I have a Poisson distribution. Depending on the context of the problem, you need to understand whether you'll apply a binomial or a hypergeometric or a discrete uniform or a Poisson distribution. Is this clear?
Yes.
Yes,
Okay.
ma'am.
Right. So now let's move on to the last module, which is I'm going to look at. Let me check whether there are any chat questions and then I'll get back.
Excuse me, ma'am.
Symmetric.
Yes, ma'am.
Okay. Yes. Yeah. Yes, please.
Can you repeat Poisson distribution again? Examples.
Okay. Let me give you an example. Just wait for a second. I'll ask you these questions. So clearly tell what is the difference.
Also, could you repeat the last point?
Last point of what?
You were discussing that we have to differentiate between binomial.
Yeah. So I'll give you an example. Just give me a minute. I have an example. I'll just ask you that question from that example. Give me a minute, please. Okay. So let me ask you this question and you should tell me whether we are going to have a binomial or a okay. Suppose I have a company, okay, that is selling clothes. Is that clear?
Yes, ma'am.
Just listen to the problem.
Yes, ma'am.
Happened here. Okay. I'm having a company that is selling clothes. It is observed, assume Amazon. Okay, that's an e-commerce company which is selling clothes. It is observed that 10% of the customers return items. Okay. On a particular day, 20 customers purchase the items. What is the chance that exactly 5 customers will return the items? What is the distribution that you would use?
Binomial.
Poisson
distribution.
Why would you use a Poisson? What are the information that is given to you?
It's binomial.
How many people return
Lambda
the
equal to
items?
0.1.
That is
5.
the people who return the item. I can call a return to be a success, or I can call return to be a failure, and persons who do not return could be a success, right?
Yes, ma'am.
And is that I'm saying
Yes,
that
sir.
it is observed that 10% of the customers return. So is the chance of customer 1 returning the item independent of the chance of customer 2 returning is independent of the chance of customer
Yes,
3?
ma'am.
What is the chance with customer 1 returns? It is 0.1, right? All of them have 0.1. I'm asking what is the chance that there are exactly 5 people? How many people have made the purchase? 20 people have made the purchase. I'm asking out of these 20, what is the chance that exactly 5 people return? So what is the distribution that you would use?
Binomial.
Binomial.
A parameter of this problem. Binomial with what is n? Small n?
Binomial.
What is small n?
Small n is 5.
Small n is 20, ma'am.
20.
Small n 5 or small n 20?
20.
K is 5.
20.
And what is
20,
P?
20.
It is 0.1.
0.1.
If I know n and P, I can find out what probability x equal to 5, which will be 20 choose 5, 0.1 to the power of 5, 0.9 to the power of 15. Is that right?
Yes,
Yes, ma'am.
Yes,
Yes.
ma'am.
Okay.
Yes,
Now,
ma'am.
if I say that, what is the probability that the maximum of 4 customers return the item? What is it I need to know?
24 into 0.13.
I need probability x is less than or equal to 4, which is coefficient k going from 0 to 4, n choose k, p to the power k, 1 minus p to the power of n minus k. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Okay. The next question I'll ask is, what is the average number of customers who would have returned? What should I do? I know x is a
Expectation, ma'am.
binomial with parameter n equal to 20 and p equal to 0.1. I find out the expectation. What is the expectation of a binomial?
NP.
NP.
What is 20 into 0.1?
2.
2.
Then average, how many people will return?
2.
2.
Is it clear? So now is it clear as to what we are looking at?
Yes, ma'am.
Right? Okay. So similarly, what you can do is the similar context. Okay. Now I'm saying on an average, 20 customers per day cancel their orders. Okay. I want to know what is the probability that the number of cancellations is exactly 20.
Poisson.
I'm telling on an average, it is noted that 20 people on a day cancel their orders. So what is the probability that x is exactly 20? So what is the distribution now? X is a Poisson with what is lambda? Average is 20. That's what I said.
20.
20. Yes,
The
ma'am.
average number of this one in a day, I'm assuming 20 people cancel their orders. So I want to know probability x is equal to 20, which is e to the power of minus 20, 20 to the power of lambda into 20 factorial. Is that clear?
Factorial. Yes, ma'am.
Yeah. So this is how you can, for the same problem, you can see that when I have modeled it as a binomial and when do you model it as a Poisson distribution. Till here, is it clear?
Clear.
Yes, ma'am. Clear.
So now let's move on to the uniform distribution. When I talk about a uniform distribution, I said again we are moving to a continuous distribution. The value that x takes in this interval is constant. Okay, so if I have the distribution, which is here referred to as a probability density function as against a probability mass function. For discrete, we called it a PMF. For continuous, you call it a probability density function. It is a continuous curve. It was not a discrete bar here. It's a continuous curve. I say that x follows a uniform distribution with A and B if this is a constant. So I have this as a constant. If that is a constant, let's know what is the value of the constant. It should be a constant. What is the area under the curve? So just as probability x equal to xi, overall xi equal to 1, I need the area of this curve to be equal to 1. That is the area of the curve is the definite integral between a to b, f of x dx. Would you all agree?
Yes, ma'am.
Right.
Yes.
Now, what is the
Yes,
area
ma'am.
of this rectangle? If this is k,
1.
what is the area of this rectangle?
1.
1.
In terms of k, what is the area of this rectangle? What is the area of this rectangle? This is A, this is B. So what is this? This is B
K by
minus
B
A.
minus A.
This is B minus
K
A.
into B.
K into B minus A. What should that be equal to? It should be 1. So what is the value of K?
1
1 by B minus A. Is that clear? So how do I give the probability distribution function? I write it as f of x, which is equal to 1 by b minus a. For A is less than X is less than B, 0 otherwise. That is what I refer to as my probability density function. Is that clear?
Yes.
Yes,
Yeah.
ma'am.
Now, when A is equal to, so some books give it as A is less than or equal to, some people write it as A. Actually, when you're talking of a continuous distribution, the probability it takes a value is assumed to be 0. So these two are the same. A is less than or equal to, or A is less than. Whereas in a discrete distribution, it makes the big difference. Is that clear again?
Yes, ma'am. Yes, ma'am.
Okay.
Clear, ma'am.
Now,
Yes,
if
ma'am.
I have a particular condition where A equal to 0 and B equal to 1, I call it again a standard uniform distribution. So I write it as X is uniform between 0 and 1. Okay. So again, I want to make the distinction that if A and B are included or A and B are not included, actually, conventionally, you can assume that both of them are included because the probability X takes a particular value for a continuous random variable is 0. So now when I have f of X is taking the value 0 or 1, again, it is called a standard uniform distribution. Now again, let's look at the cumulative distribution of X, which is uniform between A and B. Okay. Let's look at how the cumulative distribution function would look. Now again, let's look at this. I have A here, I have B here. What is the value I have till X is equal to A? What is the value of any value? What is, suppose I have a C here.
0.
It is 0. So till this point is going to be equal to 0. Would you all agree?
Yes, ma'am.
At A, what is
Yes,
the
ma'am.
value? At
1 by
A,
B minus A.
1.
1 by B
minus
minus
A.
A.
1.
Right? 1 by B minus A, right? At A, it
Yes,
is
ma'am.
what at this point, say it is at this point, what would be the value of f of X? It is going to be A to say this is a point T. It is going to be the area, right?
Yes, ma'am.
Right?
Yes, ma'am.
Into 1 by B minus A. And what is this value? T minus A. Would you all agree?
Yes, ma'am.
Yes, ma'am.
So it
Minus A
would
by B
be
minus A.
at T, it would be T minus A by B minus A at T1.
Yes, ma'am.
At
Yes,
T2,
T2 minus A by B
T2
minus
minus A
A.
by B minus A.
B minus A. So would you all agree that I can write this as T1 by B minus A by B minus A. This is a constant and this depends on where your point is here. At T1, it is T1 by B minus A. At T2 is T2 by B minus A. So for any point X between A and B, what would be the value here?
X minus A by B minus
It's going to
minus
be
A by B.
X by B minus A minus A by B minus A, which is nothing but X minus A by B minus A. Would you all agree?
Yes, ma'am.
Yes,
Now,
ma'am.
this is the equation of a straight line. Minus A, this
Yes,
is
ma'am.
y equal to mx plus some constant. Would you all agree?
Yes, ma'am.
Yes,
Agree?
ma'am.
So this is the shape of the cumulative distribution function. So for any, so you can see that the cumulative distribution function here 2 and 4 is having the shape that we just discussed with the slope as 1 by B minus A. That's what I have here, right? The slope is 1 by B minus A. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. Now let's look at what is the expectation of a continuous random variable. What was the expectation of a discrete random variable? It was over all values of X, the value into probability it was taking, right? Now here it is going to be, the expectation is, suppose I have X is between U and A and B, it is going to be X into f of X dx. You are replacing the summation with your integral. Is that clear?
Yes, ma'am.
Now I have A to B. X, what is f of X? It is 1 by B
1
minus A
by
into
B
dx.
minus.
I can remove this 1 by B minus A. This is going to be A to B x dx. What is integral x dx?
Oh, x square by
X
What is
square.
integral?
X square by 2.
X square by 2.
Definite integral between a and b, I'll have a b square
By 2
minus a
minus
square
S square by 2.
divided by 2
Yes.
By 2,
into 1 by b minus a.
which
This
is
is
A plus
a
B by
plus
2.
b by 2. So what is the expectation of a
2.
random variable? It is going to be a plus b by
A plus
2.
B by 2.
a plus
Is
b
that
by
clear? Now I can do
Yes,
the
ma'am.
same
Yes,
thing.
ma'am.
What is
Yes,
expectation
ma'am.
of x square?
Integral of
Expectation of X square
x square
into
into
X
1 minus b
cube.
This is going to be b cube.
1 by B minus A into B cube minus 50 by 3.
Okay. Now what would this
By
be?
3. B square
b
plus A
square
square
minus
minus
a.
AB.
Okay. So
Yes,
you all
ma'am.
can do that. So you can check that
Yes, ma'am.
the variances b square plus a square plus ab by 3. Is that right? So I again
Yes, ma'am.
apply
Yes,
the
ma'am.
expectation
Yes,
of x
ma'am.
square minus expectation of x square to get variance of x is b minus a whole square by 12. Not this. This is not wrong. This is right. Is that clear?
Yes, ma'am.
Clear.
Okay. Now, one of the things that you would be asked to do is, given the distribution, compute the probability. Suppose I have x is a uniform random variable, which is defined over this one. What is the probability x is greater than 1 by 3?
Greater than तो 0 से 1 by 3 में इंटीग्रेट कर देंगे तो
Greater than 1 by 3.
0
What would it be? Yeah. So what?
1 by 3
Simple.
to 1.
See,
1
I
by
have
1.
between 0 to 1.
1 by
It
3
is.
to 1.
1.
It is 1, right?
1
So I
minus the
just want this
probability.
area. 1 by 3, 2 by 3. So it is just going to be 2 by 3, right?
Yes, ma'am.
X is less than or equal to 0.7.
0.7,
It is
0.3.
just 0.7, right?
1. Yes.
0.7. Now
0.7.
here you see, this is the trick question. What would this be?
0.6.
0.6, because
0.6.
is that different from 0.3 is less than or equal to x is less than or equal to 0.9? Is the same,
Yes, ma'am.
right? Okay. Now, okay. Now this application question, you are to meet a friend at 2 p.m. You arrive
please
exactly
repeat.
on time. Yeah.
Ma'am, please again repeat third point, ma'am.
Which point? This point. I'm
Yeah,
asking
ma'am.
whether this 0.3 is less than x is less than or equal to 0.9. What would this be?
0.6.
It's also 0.6. Because for a continuous random variable, these two are same. That's what I'm trying to say. Is it clear? Because what is probability x is equal to 0.3?
Equal to which point?
0.
0. It's a continuous random variable. Now I can only define x belongs to an interval.
Okay, ma'am.
Is it clear? Okay.
Yeah.
Now you are to meet a friend at 2 p.m. While you are exactly on time, your friend is always late and will arrive at a time uniformly distributed between 2 p.m. and 3 p.m. So how late will your friend be? So what is uniformly distributed? The amount of time that you have to wait is uniformly distributed. And what is how many minutes uniformly distributed between? How many minutes are you waiting? You are arriving at 2 p.m. Your friend could arrive anytime between 2 and 3 p.m. So what is your waiting time? It is uniformly distributed between 0 and 60 minutes. Is that clear? Now, what is the probability that you will wait for at least 30 minutes?
This is 1 by 2.
1 by 2.
1 by 2.
1 by 2.
1 by
Less
2.
than 15?
1 by 4.
1 by 4.
1 by
1 by
4.
4. Very good.
1 by
Between 10 and 15? Till 35?
5 by 12. This is 5 by 12.
12.
And which is 25 by 60, right?
Okay,
Less than
ma'am.
45 minutes?
Ma'am, this is 45 by 60.
3 by 4.
45 by 60.
which is 3 by 4.
45
Is
by
that clear how you apply?
Yes, ma'am.
Yeah.
Yeah, ma'am.
Yes, ma'am.
Now, I'm just in the interest of time, I have only 10 more minutes, so I'll just skip to exponential distribution. This is something which is already done in the lecture, so you can go through it. Now, the next important distribution is what we refer to as the exponential distribution. Typically, the exponential distribution is used when you are trying to model in the inter-arrival times or service times and queues and all of that, then you use what is called the exponential distribution. So the exponential distribution basically is again given by f of x is lambda e to the power of minus lambda x. So if you look at the shape of the distribution, you can see for different values of x, how the shape of the distribution is. Now, if f of x is lambda into e to the power of minus lambda x, what is probability x is less than or equal to x? I know f of x is lambda e to the power of minus lambda x. Let me do probability x is less than or equal to a. F of a, the cumulative, this is going to be 0 to a because x takes the value greater or equal to 0 into lambda e to the power of minus lambda x dx. What would this be? Again, this is going to be lambda
Lambda e to the power minus
minus
lambda
e
x
to the
by
power of
lambda.
minus lambda x 0 to a by lambda. This cancels out, right? So what is this?
1 minus e to the power
1
lambda
minus e to the power of minus lambda a. Is that right?
a.
Okay. So the
Yes, ma'am.
distribution function or the cumulative distribution function of an exponential distribution is given by 1 by e to the power of minus lambda a. And for any a, you know that this is the shape of the cumulative distribution function. You can see that for any lambda, after a point, it tapers at 1. It can never go beyond 1 because it's a probability. It tapers at 1. Is that clear? See the shape of the
Yes.
distribution function?
Yes, ma'am.
Okay. Right. What is the expectation of this? Expectation of an exponential function is 1 by lambda. The variance is 1 by lambda square. And
1 by
this we have
lambda
done
square.
in detail. We have shown it by expectation, by integration by parts. You can show that expectation of 1 by x is 1 by lambda and variance of x is 1 by lambda square. Okay.
Yes, yes, ma'am.
Yeah. So now let's look at an application which you have to know. Suppose the length of a phone call is an exponential random variable with parameter lambda equal to 0.1. Okay. If somebody arrives immediately ahead of you, find the probability that you'll have to wait for more than 10 minutes. So x is greater
1
or equal
minus
to
e
10.
to the power minus 1.
What would that be? First of all,
1
what is
minus e to the power
exponential?
minus
X
1.
is exponential.
Lambda 1 minus e to the power lambda a.
Okay. X is denoting the length of the call. The probability that you'll wait for more than 10 minutes.
1 minus e to the power minus 1.
Okay. 1 minus of 1 minus x is 1 minus e to the power of minus 1 would be f of a, which is probability x is less than or equal to 10. I'm asking probability x is greater or equal to 10.
In this case, it will be e to the power
1
lambda.
minus.
It will be just e to the power of minus 1. Is that clear? Right. Between 10 and 20 minutes. It
E
is
to
going
the
to
power
be
minus 2.
f of 20 minus f of 10, which would be
F of 1.
F of 20 minus f of.
very good. Then you can compute that would be e to the power of minus 1 minus e to the power of minus 2. Is that clear?
Minus 1.
Yes,
Okay.
ma'am.
Right. So I think this is what I started out to do. We started by reviewing what is a random variable. When you talk about random variable, we introduced both discrete and continuous. Remember, discrete variable is when you are counting. Continuous variable is over a interval. So when I have discrete, I have x taking a value. When I have continuous, I have x belonging to an interval. This is the first thing. Is that clear?
Yes, ma'am.
Now the next thing is I have a distribution. This is probability x PMF. X takes the value x1, x2 with probability x equal to xi. Here x belongs to A to B. So I have what is called a density of the random variable. Third thing is summation probability x equal to x over all the values x is equal to 1. The similar thing is a to b f of x dx is equal to 1. Till here is it clear? The cumulative distribution function is probability x is less than or equal to a. Here I found it was a discontinuous step function. Here you saw that it was a line for a continuous uniform random variable. For an exponential, it took this shape. Then we define the expectation of x is summation x into probability x is equal to x. Here, this is going to be x, f of x dx over the range that you are defining. If it is a to b, it will be a to b. Variance of x, the computational formulation was expectation of x square minus expectation of x whole square. Compute expectation of x square will be x square. Similarly, expectation of x is equal to x into f of x. Expectation of x square would be x square into f of x over a to b. So you can see that I can apply the variance of this random variable. So this is discrete and this is in continuous case. When we looked at the discrete case, we looked at basically we started with Bernoulli random variables. Then we moved on to binomial. The key point we noticed was the IID. Then we moved on. Then we also looked at discrete uniform. Then we looked at hypergeometric and Poisson. For each one of them, we computed what was the probability mass function, what was the expectation of the random variable, and what was the variance of the random variable. And we looked at application. This is what is expected to know. In the continuous case, we looked at the continuous uniform and a continuous exponential distribution. Again, we looked at what was the probability density function, what was the cumulative distribution function, what was the expectation, what is the variance, and we looked at application of the formula to problems. So this is what we have revised today. This is 4 weeks content which we have tried to revise in 2 hours. If there are any conceptual level questions, please feel free to ask at this point.
Ma'am,
Yeah.
in the end term examination, normal distribution will not come.
1 second. Prerna, can you answer that question?
Yes, so for the end term exam, normal distribution will not be coming.
Yeah.
Okay, ma'am. Thank you.
Ma'am, will this
Sorry, ma'am,
PDF
which
be shared with
distribution
us?
will not come?
Please wait for the person to finish the question. Yeah.
Ma'am, will this PDF be shared with us?
Yeah, I can share this PDF, not an issue.
Yeah, so this PDF will be uploaded on the portal. So you can access from there.
Yeah.
Where in the portal precisely?
Under the supplementary content.
Okay.
Okay.
Ma'am, in the week 12, only 12.1 to 12.4 will occur in the examination.
Prerna,
So
can
you
you
have,
answer that question?
yes, ma'am. So you have to cover all the topics except normal distribution. Okay.
Okay, ma'am. Thank
You
you.
can just leave the normal distribution, else you have to study.
So it's only normal distribution that will not be part of the end term exam, right?
Yes.
All right, thank you.
Excuse me, ma'am, I have a doubt in
Yeah.
hypergeometric distribution.
Yeah.
Yeah, for the variance, there is an extra term. There is n minus n by n minus 1, right?
Mm-hmm.
So I did not understand what was the significance of that. It is np into 1 minus p, right? Normally.
No. See, I said that as this n by n, right? This is the hypergeometric formula. Okay.
Mm-hmm.
I said that you can view this point as n into m by n into 1 minus m by n. Okay, I can write this as 1 minus m by n. This portion is the same as 1 minus m by n. Would you agree?
Yes, ma'am.
Right? And this I can write as 1 by n divided by 1 by 1 by n. This portion.
Yes, ma'am. Yes, ma'am.
Now, depending on what is this n by n, suppose this n by n is very, very small, say 1%, 0.01, then what would happen to this?
It would tend to 1.
1. So you can see that when this n by n is very small, okay, 0.1%, you can see that the hypergeometric and the binomial distribution almost have the same PMF. Would you agree?
Okay. Yes, ma'am.
When it is 0.05, it's almost the same. But you see that when it becomes 10%, you see that they are differing a bit. You don't see
It's
that they are
peaking.
coinciding, right? But when it is
Yes, ma'am.
becoming more, 50%, you see there is a distinct difference between the hypergeometric and the binomial.
Okay. Okay.
That's
Okay.
what
Got
I
it.
wanted to highlight. Is it clear?
Yes, ma'am. Thank you.
To continue the same slide, sorry about my name. Here it is actually taking at 50%, it's almost taking a bell-shaped curve. Why in the previous cases this actually the shape? I mean, I'm missing that part.
That is
The shape
because
is
your
completely
n is very high. Here it is very slow, right? 50. This depends on the size of your sample also.
okay. Thank you.
Okay. The size of the sample here is only 5. Then it becomes 25. Then it becomes 50. And the minute it becomes very high, it's taking the shape of a bell-shaped curve. Is that clear?
Yeah.
Yeah. Any more questions? Okay. No more questions. I think I'll stop here. Thank you all for your patience and I think enthusiasm of attending 6 to 8 in the evening. Wishing you all the best. Okay. Thank you all.
Thank you, ma'am.
Thank you all.
Thank you, ma'am.
Thank you all.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Thank you.
Thank you, ma'am.
Can I get the recording?
Thank you.
Ma'am, can I get the recording?
It's already in the YouTube.
I'm not sure whether the
In the
record.
YouTube
These are
Google
things
Calendar.
administrator. You can check with Prerna. Prerna, is the recording made available?
Yes, we can access the recording. So from calendar, you can get the link of the YouTube video.
But please make only people who are actually signed for the course access the recording. Okay.
Oh, okay.
Oh,
Sure.
so
Whatever is the policy, I really don't mind. Okay. Yeah.
okay, sorry, ma'am. I don't know that.
Yeah.
Actually, I was late today, so I
Okay.
don't.
Yeah, not an issue. I don't have a problem. As long as you are
Yeah.
willing to learn, whenever you learn and from wherever you learn should not matter. Okay.
Ma'am, can I just say
Ma'am.
something?
Yeah, please.
Ma'am, I'm Arabhi and I just wanted to say I'm such a big fan, ma'am. Like, this is my first time attending this live.
Okay.
Mine too, also.
It feels
Mine
so
too
good,
Be a
also.
ma'am.
big fan of the subject, not of a
Yes,
person.
ma'am.
Okay.
I'm also a
Great.
big fan.
No, ma'am, but listening to
You
you
all
live.
should be big fan of the subject, and if I've been able to motivate you to learn statistics, I consider myself to be good. Okay.
Definitely,
You
ma'am.
should learn statistics and enjoy statistics. That is what is more
Yes, ma'am.
important.
You've
Okay.
been a big motivator. And
You made us
even-
enjoy statistics.
Yeah,
Yes,
you
ma'am.
should enjoy
I
statistics. That's it.
watched all.
Yes, ma'am. It's like a fangirl moment because, to be able to listen to you live after listening to your recorded sessions, it feels like a dream.
Excuse me, ma'am.
Thank you so much,
It is
ma'am.
also, like, seriously, it is.
Excuse me, ma'am.
Okay.
The first conversation.
I'm not
with
a
the
celebrity, ma. I'm a teacher and I enjoy being a teacher. Okay. So I want students. I
Ma'am,
don't
you
want
look like a
fans.
celebrity.
Excuse me, ma'am.
Yeah.
Ma'am, you are the
Ma'am, can you hear
celebrity
me?
first.
Okay. Yes, somebody has raised their hand.
Yeah.
Ma'am, can you
Statistics is
hear
my
me?
subject.
Pardon?
Statistics is my favorite subject.
Very good. Please learn the subject well. We hope to see all of you succeed in your life. Wishing you all the best. Okay.
Thank you,
Thank you
ma'am.
so much, ma'am. You were
Thank you
such
so
a,
much.
so much
you.
fun.
Thank you. All of you do well. Okay. Right.
Yes.
Yeah.
Thank you.
Because of
Yeah.
you,
Thank you, ma'am.
statistics
Thank you so
became
much.
my favorite subject.
Do well. Do well. Okay. Learn well and do well. Okay.
Ma'am, I just
Thank
had
you all.
one more question, ma'am. Ma'am, are you a Tamilian?
Will that make a difference?
No, ma'am.
I
I just
speak
wanted
Tamil.
to
Yeah. Yes.
Yeah,
Yes.
but
Yeah.
I'm also
Okay.
Tamilian.
Okay. Okay then. Thank you all. Good night.
Thank you,
Take care
ma'am.
and all the best. Yeah.
Thank
Bye.
you.
Bye.
Thank
Yes,
you, guys.
ma'am.
Good night.
Good night. Yeah.
Good night.
Namaste, ma'am.
Good night.
Bye, ma'am.
Bye. Bye.
Yeah, thank you, ma'am, for the session today.
Prerna, is it available on the YouTube right now? Like
Yes, so
I'm
you can.
already watching on the YouTube, but after this session is over, so it is working on a YouTube or
Yes, yes. So
like
you can
there is
access the
also.
link. Yeah, it will be working.
Okay, thank you.